Yeah, thank you, Sang-il, for inviting me to give a talk here. I would like to talk about the maximum induced matching width, so which has a stronger expressibility than rank width. And this was invented in 2012 by Martin Bussell in Bergen. And so we explored several computational complexity of the problems parameterized by Mim-width. So I would like to introduce the sketch of the story. And this is based on the joint work with Lars Jaffke, Torstein Strømme, and Jan Arne Telle in Bergen. So we had these 3 papers accepted in last 10 this years. So the first 2 series were work with Lars and Jan Arne, and then third is joint with Torstein as well. So the talk consists of these things. So I first focus on introducing Mim-width using branch decomposition. But before going to the Mim-width, so I will give you the overview of the previous parameters, branch width and rank width, and we will compare with the Mim-width. Especially, we will see that how independent set can be solvable on graphs of bounded other width parameter, and also see that why they can be tractable on graphs of bounded Mim-width. And actually, not only independent set is tractable on graphs of bounded Mim-width, you can see some general set of problems that can be solved in polynomial time on graphs of bounded Mim-width, so-called locally checkable problems. So I will tell you what they are. And then, so when I visited the Jan Arne, so that's all we know at the moment. And then we try to look at the other types of problems, like feedback Vertex Set problems and linkage problems and so on. So we have some results on the connectivity problems, and we will give an overview of the classes of bounded Mim-width. So this will be the contents of the talk. Yeah, so width parameter is usually designed so that if the width is small, then graph can be decomposed in the natural way, so that you have some tree-like structure or path-like structure. And you know the tree decomposition is an example. But branch decomposition is some general decomposition scheme that can be used to define for various parameters. So I will introduce branch decomposition. So here is an example. So you have given a graph, and branch decomposition of this graph consists of two things. So firstly, you have a tree, and then also that you have some assignment of the elements in the graph to the leaves of the tree. Like here, so usually we take either vertex set or edge set. So here the example where the vertices of the graph G are assigned to the leaves of this tree. So this is one decomposition of the graph. And then to measure the complexity of this decomposition, so we use some function f. So consider some function f from the ground set to some real number. And so each edge is assigned the value fa, where a is one of the part divided by some edge. So whenever you choose some edge there, so the elements are divided into 2 parts, and then you measure the complexity between these 2 parts by computing this f of a. So we can take many types of function f, and we solve this decomposition is that the maximum values among all edges there. So which means that we say that the maximum value is small, then this decomposition is good. And we solve this graph is that the minimum is among all branch decomposition, which means that if a graph has a small width, then you can decompose in a good way.
So do you want to require the function to be symmetric?
Symmetric. Yeah, at least. Yeah, sure. And so one example is that actually Roberts and Seymour defined this branch decomposition and branch width. And for this width parameter, the ground set is edge set. And then for some subset of edge set, So you consider the number of vertices meeting both A and the rest. So in this example, these 4 purple edges are my set A, and then the rest blacks are the rest. And then you can see that the 4 vertices, B, C, D, E, meeting these both parts, right? So here f of A is 4, and then you can imagine that you decompose the branch decomposition of where edges are the label on the leaves, and then for every edge you partition the edge set into 2 parts, and then you measure this. So this along this you define the branch width, and this notion is equivalent to tree width of the constant. So the other notion is the rank width. So for the rank width, the ground set is a vertex set, and so whenever you have a partition of vertex set, so you introduce some matrix, which is the sum matrix of the adjacent matrix, where the rows are indexed by one part and columns are indexed by the other part. And then you put the 0 if they are non-adjacent, and then put the 1 if they are adjacent. And then you compute the rank over the binary field. So here the example of the matrix, and then the rank is 2. So note that we compute the rank over the binary field. So basically, what they want to is that you want to restrict the number of distinct rows, actually. So if the rank is k, then because we compute the rank over the binary field, you may have at most 2 to the k distinct rows and distinct columns. But the usefulness of the rank is that it will be a submodular, so you can do something better than just counting the number of distinct types. So this notion is equivalent to some classical notion called the clique-width. So rank is usually the parameter that want to capture the simplicity on the dense graph classes. Yeah. So I will just simply compare what is the idea for computing the independent set for the graphs of bounded branch width. So imagine that you have a bounded branch width, branch decomposition of bounded branch width, and then this means that if you look at the edge, then you have a small separator. So the edge set are divided into 2 parts, and then the only small vertices are intersect in both parts. And then what you can do is that you can guess the intersection of the solution with this small part here. So you can guess all the 2 to the w many possibilities there. And then whenever you guess some partial solution, you ask whether there is some set I where the S union I is independent set. So among them, you keep the maximum guy, and then this will be enough. So this is basically the idea to obtain an independent set for the graphs of bounded width. So you can have a 2 to the w algorithm. For the rank width, what you do is that, so as I said, if your rank is bounded, then number of distinct neighborhood types to the rest is small. So if you want to recursively construct the independent set on the left-hand part, what you can ask is that on the right-hand part, you guess the parts that have some vertices in my independent set. So you guess all possibilities, and then, for instance, I guess these 2 parts that have an independent set. Then here, so you cannot use this part because they are completely adjacent, right? So you're looking at the maximum independent set I, which have no edges to the guessed parts. So this kind of scheme can be used to obtain a maximum independent set on graphs of bounded rank width. So actually, you can do better than just guessing all the partitions. Okay, now, so we want to go to the maximum induced matching. So it's a different type of complexity of a curve. So you have some vertex set S and the rest. What you can first is that you forget the edges in S and edges in G minus S. So this is denoted by G, S, comma, the rest. And sorry. Yes. So I say that in this bipartite graph, so the matching V1, W1, V2, W2, etc. is induced if there are no other edges between them. So there are no other Vi, Wj edges. So the maximum size of such an induced matching is denoted by Mim-S. So we will call Mim function of this vertex set. Is this clear? Yeah. So this is the important part in the talk you should understand. And so the Mim-S is just the branch. So the decomposition is a branch decomposition, and then function is taken by Mim function of a vertex set. And then we will denote by Mim-G as a Mim-S of graph. And then you can easily see that the rank is bounded, then Mim-S is simply bounded, because as I said, if the rank is bounded, then you have a number of the bounded number of distinct neighborhood types to the rest when you have a count. And then if you choose induced matching between them, so you cannot have two endpoints on the same part, right? Because then they have the same neighborhoods on here, so you should have an edge to here, right? So you cannot have induced matching. So induced matching is bounded, but the other direction is not true. So yeah, probably the motivation of the Mim-S is came from interval graphs and permutation graphs. Yeah. So I will say that I will prove that why interval graphs have found Mim-S actually 1. So the interval graph is intersection graphs of intervals in a real line, which means that some graph, the vertices are represented by some intervals in the real line, and then the vertices are adjacent if you don't need the corresponding intervals cross. Yeah, so this is interval graph, and then it's interval model. And permutation graph is also an intersection model where you have two parallel lines, and then you have a set of lines between these two given real lines. And then the intersection graph of this is a permutation graph. Yeah. Let's consider this interval graph. And then you can even generate some linear ordering so that whenever you cut some point in the left and right, then the mean function of the left-hand side is always 1. So the natural way to generate the linear ordering is that ordering by the left point of each interval. So currently the left point of A first appears, so A is the first guy, and then the left point of B appears next, so B is the next guy. So you can give ordering A, B, C, D in this example. And then assume that there is a matching between from the left-hand side to the right-hand side. So like a V1, W1 and V2, W2 is a matching. And suppose that V2 is non-adjacent to W1. Then you can easily see that V1, because it starts from the left-hand side, you have to go to this right-hand side to this left-hand point of W1 to meet W1, right? And then the other way is that W2 should go to the right-hand side of V2, so they should intersect, right? So they have to have a V1, W2 edge. So which means that you cannot have an induced matching of size 2 in this ordering. So this gives that actually, so I didn't define the linear Mim-S, but it says that the specific type of branch decomposition have width 1. Yeah, so interval graphs have linear Mim-S 1. So now we can think about the independent set on graphs of bounded Mim-S. So it's a very old result that Gabriel showed that actually not only interval graphs, for Kodak graphs, independent set is linear time solvable. We proved this. So the natural thing to think about is that can you generalize to graphs of bounded Mim-S, right? Because interval graphs have one of graphs of bounded Mim-S. So probably we can more generalize to the graphs of bounded Mim-S. So the first observation is that there are n vertex interval graphs with rank is at least almost square root n. So which means that so its construction is like a grid things. So you can generate some grid type guys where that all the between guy you have some chain graphs. Then you can easily see that the rank is like almost square root n of the n vertex graph. So if you apply the rank list algorithm, so the best algorithm was a 2 to the w square, so it's like a 2 to the n algorithm. So it doesn't make sense so much. So but for Mim-width is quite stronger than the rank list. So probably FPT algorithm is difficult, but our guess is that we might expect some n to the f of w time algorithm for some f. So of course, if f is very high, then it's not at all practical. But probably we can obtain f is like linear or square, something like that. So this is my guess. So so summary is that Mim-width is defined using branch decomposition, where complexity is computed by maximum induced matching of a bipartite graph. Interval graphs and permutation graphs are bounded Mim-width. So independent set is polynomial time solvable on graphs of bounded Mim-width. And are there more algorithmic applications, and which graph classes are bounded Mim-width? So at the last sections, we will consider some more classes of bounded Mim-width. But I just summarized that there are lots of classes known to have a bounded Mim-width. But this is quite surprising because for tree-width and rank width, there are some few classes that have interesting classes of bounded tree-width and rank width. But for Mim-width, there are lots of well-known graph classes that have bounded Mim-width. So we will come back to here again. So we first consider the algorithmic applications.
All of them have they have a bounded, unbounded rank?
I think so. Yeah, I think so. Yeah. I haven't checked carefully, but almost them are generalizations of interval graphs in some sense. Yeah. Yeah, not all of them. Like convex graphs are independent, I guess. Yeah, so we first consider the locally checkable problems. So if you understand the locally checkable problems in this talk, then it's successful. So yeah, so it's defined by Jan Arne Telle and Andreas Prosperski in 1997. They want to generalize like independent set or dominating set problem to some general set of problems called the locally checkable vertex set problem, and like a Q-coloring problem to the vertex partition problem. So for all the algorithmic result, we assume that the decomposition is given as input. So this is just comment. Maybe I missed in the assumption. Yeah. So we come back to the independent set. Suppose that you have a cut of a small mean function. Like if a mean function is 1, it's you can see that the 2p2 free graph is the chain graph, right? So you can have like arbitrary large chain graphs. So how do we do on the independent set in this situation? So what we can naturally define is that you want to give an equivalence relation of the partial solutions. Like we say that the S1 and S2 in the A part are equivalent for the independent set. If for every T on the right hand side, if S1 union T is independent set, depend on if S2 union T is independent set. Like this is a quite natural definition. So if this is since this is a nice equivalence relation, so you can take at most one of the solutions in the equivalent classes, right? So you can take a maximum among them because you don't have to keep the others, right? But this is quite depends on the independent set problem, right? So you can actually define some refinement of this equivalence relation without really relying on the independent set. So we can like denote by S1 equivalent to S2. Yeah. If for every vertex outside, if we have a neighbor in S1, depending on if we have a neighbor in S2. You can easily see that if two sets are equivalent in this sense, then they are equivalent for this independent set, right? Because assume that S1 union T is an independent set, which means that no vertex in the T has a neighbor in S1, right? So each vertex has no neighbor in S2 as well, right? So S2 union T is common independent. Of course, we assume that S1 and S2 are each independent. Yeah, both are independent. So it's enough to keep one partial solution for each equivalent class of this notion. And the question is that how many equivalent classes there, right? So the nice result by Belmont and Vatshelle in 2013 is that this number of equivalents, so we denote by NEC as the number of equivalent classes. So this number of equivalent classes is bounded n to the mean function of A. And the other paper by Bush and Telle Vatshelle is that if you have a branch decomposition, and then whenever you look at the cut, the maximum neighborhood equivalence classes are denoted by this, and you can solve this independent set in time n to the first times this to the third. Where if a Mim-width is bounded, then like a Mim-width is 2, then you can apply n to the 2 here, right? So this will give anyway polynomial time algorithms, right?
So NEC equivalence A is the equivalence class of the partitions A.
Yeah, you have a fixed A and the rest,
Right.
and then number of equivalence classes only.
Can you show the definition?
In the equivalence relation?
Yes.
Okay. So the equivalent, if for every V on the right hand side, V has a neighbor in S1, depend on if V has a neighbor in S2.
All right.
Yeah.
So you want to look at the equivalent classes of this equivalence relation, and then so easily see that you can take at most one partial solution among them, right?
You define T comma sigma.
Yes.
You consider all ordered by partition and takes
Yeah.
the maximum.
Yeah, actually, yeah, if you have a partition, you consider it. There are some relation between them. But yeah, easily you can consider all paths there. Yeah, so probably this part
It is not that difficult. You can see the paper, but probably this part, the first theorem is quite interesting. So I want to introduce this. I want to give an intuition about this. So what they prove is that actually you can characterize when Mim function is at most k. So you can prove that so they prove that the Mim function is at most k depending if for every set A, for every set S in A. So there is some subset R of size at most k, such that they have the same neighborhood outside. So yeah, they are actually equivalent, but to have this bound, we only need this direction, I guess. And yeah, suppose that this part, right-hand part, does not work. Okay, which means that there is some data set S such that for every set of subset of size at most k, the neighborhoods are different, right? Oh, sorry. So among the data set, you choose inclusion-wise minimal set S, such that for every subset of size at most k, the neighborhoods are different. But then you can easily see that this size of set S is bigger than k. Because if this set is size at most k, then you can take R is equal to S. Then they have same neighborhood and size n plus k. So SS size bigger than k. Then you can easily see that because of this minimality, each vertex has a private neighborhood on the right-hand side. So maybe I can draw a short picture. Yeah. So this is A, and this is A. So you look at the set S here, right? So for each vertex, if all the neighbors of this guy is dominated by this part, then you can take a smaller set to claim that. So otherwise, you have a private neighborhood of each vertex. Actually, this gives an induced matching. So yeah, so this gives an induced matching of size bigger than k, which contradicts the assumption. Yeah. So this is a nice idea, I think. So what you can see is that any subset is equivalent to some set of size n plus k, right? Because they have the same neighborhood on the right-hand side. So you can look at the n to the k sets to see the all equivalence, the number of equivalence classes. Yeah, so you can take any set S. So this R should be equivalent to S because they have the same neighborhood on the right-hand side. Yeah, I think this is quite essential idea for using Mim-width in the algorithm. And so yeah, this together with the second theorem will give an algorithm. But actually, they can generalize to the sigma row set problem, where that S is a sigma row set if for every vertex in S, the number of neighborhoods in the S is in the sigma. So sigma and rho are the subsets of set of integers, set of non-negative integers. They can be infinite or finite, so no matter. And for every vertex outside of S, the number of neighbors on S is in the row. So the example is that for independent set, so you can express this sigma row where sigma is 0 because in the set you don't have an edge between them, right? So you want to force that you have a 0 neighbor in the set, but the row is taken by n because we don't care about the edges between the inside and outside. But for does n contain 0? Yeah, yes, so n is non-negative and n plus is a positive integer. Yeah. And for the dominating set, the inside doesn't matter, but you want to have at least one neighbor to the S, right? For every vertex outside, you want to have at least one neighbor. So you give a positive integers here. And then actually by taking the combinations, you can express many problems like induced matching and induced deregular subgraphs and so on. So I will not define the integer d. It's slightly technical, but what you can do is that actually to solve each of the problem, you can take some generalization of this equivalence relation to some related with d. So we say that S1 and S2 are d neighborhood equivalent. So this is a name. For every vertex in the outside, if the neighbors are at least d, then we don't care. Both have to have at least d, and the neighbors are less than d, then they have to have a same neighborhood, same number of neighbors. And then, so for each pair, so you can define some constant d, and then so what they prove is that it's enough to see the d neighborhood equivalent classes. And also the other set of problems is that the DQ partition problem, where so you have a Q by Q matrix, where each entries are subsets of n. So it's like a generalization of a sigma row set. But now you look at the partition, and then the partition of a vertex set is a DQ partition. If for every vertex in the VI, the number of neighborhoods on the VJ should be certified by the sets in the DQ I, J index. So one can express Q coloring by taking 0 in the all diagonal, because you don't want to have edges in the same colors, right? And then the rest are just n. And then you can define an H homomorphism problem in the natural way. So you just consider all the vertices by column and rows and so on. And not only that, like H cover problem also you can define. Like this is a locally isomorphic. You assign, so each vertex of V in G is assigned to some vertex in U, such that they have the same degree there, and the coloring or colors of neighbors are they're corresponding to each other. And many more problems can be expressible, and these two types of problems are called the locally checkable problems. And so what they prove, the Belmont and Vatshelle actually proved that the D neighborhood equivalent classes the numbers are bounded by n to the D times the Mim. So because D was fixed by fixed integer by some given problem, so it's fine, and the Mim function is bounded, so you can adapt to this algorithm, okay, to have a polynomial time algorithm. Yeah, this is a nice idea. Yeah, so this is the status when I visited Jan Arne Telle. So he explained me the problems, and then at the time nothing was known except these locally checkable problems. And then we tried to look at the algorithm for a feedback vertex set and induced paths and disjoint paths and so on. Especially, so I read this paper by Jansen, Raman, and Vatshelle, named Parameterized Ecology of Feedback Vertex Set, which was an interesting survey of feedback vertex set parameterized by many parameters. And then they said that the complexity of feedback vertex set parameterized by Mim is an interesting topic. So I was intrigued by this paper. So I can explain some idea of the set of problems and then ideas that how to solve those problems. So the first problem that I look at was the longest induced path problem. So you want to find the longest path which is induced. And you can easily see that any induced path cannot cross too much the cutoff small Mim function. If you cross many times, you have a large induced matching, right? So you can guess how the induced path can intersect on there. So it's bounded by almost Mim function. So you just look at all the possible intersections over there, and then we say that we have some connections to say that these guys are connected to here, and this guy is connected to here, and so on. And then so we ask whether this can be realized, right? This looks like very simple, but actually there are some technicality where that maybe this path can still use some vertex which have a neighbor to here, right? Because this is not all the edges in the cut, right? So how to forbid them? So guessing such a part is like it's 2 to the n, right? So it looks like not good. But very interesting point was that if there is a solution, so there is a solution avoiding the vertex cover of the remaining bipartite graph, right? Because we want to so this is exactly the part that I want to use as an induced path, right? So all the other edges I don't want to use. So there should be some minimum vertex cover which avoid this solution. But the number of minimum vertex cover in the graphs of bounded Mim-width is bounded. So we can enumerate all the minimum vertex cover there. And then, so the table consists of the guessed part in the middle, comma, some vertex cover in the rest bipartite graph. And then you do a dynamic programming using this. So this minimum vertex cover result is in the Vatshelle PhD thesis. Yeah. So we show that the longest induced path can be solved in time n to the linear in Mim function. And previously, only known algorithm was interval graphs. I mean, for graphs of bounded Mim-width. And so you can easily ask whether what if a non-induced version, right? So the Hamiltonian cycle problem is related to the longest path problem. And then we can show that the Hamiltonian cycle is NP complete even for the graphs of linear Mim-width 1. So it's a Mim-width 1, I mean. It was quite interesting because the Hamiltonian cycle is polynomial time solvable on interval graphs and permutation graphs. As at the beginning, we guessed that so at least for linear Mim-width 1, you can do something, but we figured out that actually it's NP complete. But the construction was given in the previous paper. We just checked that they have a linear Mim-width 1. So actually it says that the linear Mim-width 1 is way bigger than just interval and permutation graph.
Okay, can you give a canonical example of disjoint one or even Mim-width 1, which is not a linear?
For linear Mim-width 1, so we will go back there. So convex graphs are some other graphs of bounded linear Mim-width. But we couldn't characterize the linear Mim-width 1. So this is interesting open problem. For Mim-width 1, there are lots of 3, and also leap power graphs are Mim-width 1. So yeah, so we will go back there. And the other similar variant is that induced disjoint passive problem. So you have a set of terminals, pairs of terminals. You want to link the terminal by passes, where so they are, of course, they are disjoint, and also not only disjoint, there are no edges between the two distinct passes. And you can easily see that the union of this disjoint path cannot intersect too much on this cutoff small Mim function, right? So in the same flavor, and you can solve some. So previously, the Global, Pallasma, and Lewin proved for the 83 graphs, polynomial time solver on 83 graphs. This includes the permutation interval graphs and trapezoid graphs. But other than that, so we give a polynomial time algorithm. So it's known to that disjoint path is NP complete on interval graphs. So disjoint path is just NP complete. So number of terminal is part of it. It's not fixed. Yeah. So we can simply induced disjoint paths problem can be used to solve H-induced subdivision problem, where you want to find the subdivision of some picked graph as an induced subgraph, because you just guess terminals and you want to link by disjoint paths which have no edges between them, and so on. And then just we can reduce to the induced disjoint path problem. So this is also mentioned in this 83 paper. The next problem is the feedback vertex set. So there are some interesting points on the feedback vertex set problem. So the problem is just to remind that find the minimum size set S such as G delete S has no cycles, right? So it's quite an interesting problem. There are lots of graph classes that are solvable in polynomial time. Yes, so you can consider the feedback vertex problem as finding a maximum size of induced forests, right? So it's related to induced subgraphs, right? So you can do something, but it's quite non-natural if you start to think about. So assume that you have a graph of bounded mean function. Can you restrict the number of vertices crossing the two parts of some forest? No, because you can have a huge stars where the center is in here, and then the leaves are on the left-hand side. It doesn't produce large induced match, right? So you have to do something. Does it make sense? Yeah. So many leaves can attach it to a vertex, which doesn't produce large induced matching. So we devise some notion of reduced forest, which is obtained by removing leaves. Yeah. So what it can show is that if a forest has a bounded maximum induced matching, and then the R is the reduced forest of a given forest, then R has a bounded number. So you can imagine that, because yeah. So I want to get this reduced forest in the crossing part. So this is a picture taken from the paper, and yes. So if you have a cut A and the rest, so I want to guess that this R part for the reduced forest, and then I also take a minimal vertex cover in the rest to forbid the other kind of edges, and then, but because you can have some leaves there, right? So there are some technicalities dealing with these leaves, but so we can show something about this. Yeah. So.
About this minimal vertex cover, actually, I didn't get it clearly
from
the
there?
from
Okay.
the previous.
So,
There is it. Yeah. So suppose that this is a cut of a small mean function, like A and the rest. So for instance, feedback vertex problem, you want to find the forest, right? So I guess some forest here, right? And then you might ask whether that in this part, you want to find some maximum forest whose intersections are this, right, on the curve. But actually, we guess that this crossing part, then you might have some guys having a neighbor to this part. Still, there are some edges to the right-hand part, right? So also, these guys can be used in the later, right? So we don't want to have this. But if there is a solution which really use these edges, then so you don't. So for the other edges, you don't want to use this, right? So there is some solution avoiding the vertex cover of the remaining bipartite graph. Because suppose there is a solution, yeah. So like this is a solution, and if this is a solution on the A part, then this part is not taken in the rest, right? Shouldn't be taken as a rest, right? Otherwise, this edge is used, right? So yeah, the complement of independent. Yeah. So if this is taken as a solution, then I don't want to use. So this solution is avoiding this part. So you put this vertex as a vertex cover, and so yeah. So on the other side, so you first guess about all the vertex cover, and then you want to find the solution avoiding this vertex cover. Yeah, the number of vertex cover is related to the number of independent sets. Yeah, because yeah. So actually, we can prove for the weighted version. Actually, the Benjamin Burgos and Mamadou Kante, actually they formulated this problem in some advanced use of d-neighborhood equivalence. So they explored more and more problems using only d-neighborhood equivalence. with some analysis, and then they can show that period vertex set actually can be within that framework. And then, so when it's submitted to the conference, we post the open problem for the subset period vertex set. Subset period vertex set can be solved in polynomial time on graphs of bounded Mim-width. This was recently proved by Progonox and Papadopoulos and Jan Arne Telle in this year, WG, I guess. So they claim that they can solve in n to the Mim square. So they also use d-neighborhood equivalence in some sense. And then previously, this Papadopoulos and then Zimas in 2017, they proved for interval and permutation graphs. But they generalize to the graphs of bounded Mim-width. So, So the last problem that I want to mention is the distance R version of the locally checkable problem. Just the example is that the distance R independent set problem, where you want to find the vertex set whose distance is more than R. Pairwise distance is more than R. So it's the same as finding an independent set is in R power of graph, right? R power means that you add an edge if their distance is then most D. So you don't want to have an edge in the R power of graph. But we don't know whether R power of a graph has bounded Mim-width or not, right? But we have a very interesting result that so no matter take some R power, the Mim-width doesn't increase more than twice. So it's very funny because for rank width or tree width, they have a bound, but the powers of bounded tree width have bounded rank width, but depends on the original tree width and the power. And then powers of bounded rank width is again bounded rank width, but also depends on the original rank width and power. But for Mim-width, it doesn't increase too much, whatever you take a power. So this is quite powerful. So we can just take R power and then do an independent set problem. Yes. So you can do for every distance R types of locally checkable problems. Yeah, this was the. Actually, this proof is quite pretty, I guess. But, yeah. Actually, the other part we can think. So you might ask me about the FPT algorithm, but for me, Global and Raymond recently they think about the H graphs. We will explain H graphs later. Anyway, using them, so they proved that independent set and dominating set are W1 hard. And then we adapt almost the same idea to say that the feedback vertex set is also W1 hard. So you cannot expect the FPT algorithm with some assumption. Yeah. Okay. So we want to go to the class of bounded Mim-width in more detail. So this might be another interesting part. Yeah, Belmont and Vatshelle introduced many graph classes that have bounded Mim-width. So interval graphs are permutation graphs are natural, and then circular arc graphs is that the intersection of arcs on the circle. So it's like interval graphs, but you merge the endpoints as a circle. So it's a generalization of interval graphs, and also circular permutation graphs are also similar. So you merge it to the two circles, and then intersection of the lines there. And trapezoid graphs are the so you have two lines, and then so this one trapezoid is one element. And then, so you have a set of trapezoid, and then you look at the intersection graphs of them. And then, so these graphs are naturally bounded Mim-width. Then K trapezoid graphs are the not only have two lines, you have K lines, and then so one element looks like this. So it's a union of parallels. So correct. connecting them, and then intersection graphs of them, and also circular version. So these are the similar similar with the interval and permutation graphs. And the other graphs are convex graphs. Convex graphs are the bipartite graphs with the two partition x and y, where x has some linear ordering, and the neighbors of every vertex of y are consecutive on x. Yeah. So you have a y, you have x, and then this is a linear ordering. Then the neighbors are just consecutive like this. Something like this. Yeah. So this is a convex graph. Then you can give us some ordering where, so you take vertices on the x, and then whenever you end with this ordering, you put this and the next vertex, and so you can give us some linear ordering where the mean function is small. Mean function is 1 actually. And k polygon graphs looks like a circle graphs, but you have a k polygon. So like a k polygon, and you have a set of chords. So it's the intersection graphs of chords in the k polygon. So k polygon graphs have a bounded mean-width, but circle graphs is not. Circle graphs have unbounded mean-width.
K polygon or regular?
They are, I think, equivalent because just stretch.
Convex graph linear mean-width.
Yeah.
And interval graph also has linear
Mean-width
mean-width.
1. Yeah.
Okay, so is there a case where linear mean-width is large but mean-width is bounded? Like among the
Three.
classes?
Among them.
Yeah, among these classes.
I think most these guys are bounded linear mean-width.
So when you prove that they have bounded mean-width, you actually produce a linear mean-width.
Yeah, so Belmont and Vatshelle, I think, proved just the linear ordering of classes in the natural way. So when I visited Jan Arne, so we tried to think about what is the general classes where that is the unbounded linear mean-width and bounded mean-width.
The other thing of intersection graph is the H graphs. So they use the H graphs to prove W1 hardness. And H graphs is, so interval graphs are the intersection graphs of intervals in a real line, right? But you can generalize to some subdivision of some fixed graph. So underlying graph is some H. So for instance, H is like a diamond. Then you think about some subdivision of a diamond, and you look at some connected subgraphs there. Yeah, something like this. So you have a set of connected subgraphs in the H. It's a H subdivision, and then you present intersection graphs of them, and they have naturally bounded mean-width. I didn't carefully check, but I think in the paper it just say mean-width. I have to look at it. Good. You can check. And what he proved, what he explored was actually graph powers, and I already mentioned that the powers of graphs of mean-width K is at most 2 times the mean-width of the original graph. But also for the forest, if you take any power of a forest, then still have a mean-width at most 1. So in particular, the leaf power graphs are you take a power of the tree and then you take a leaf of the original graph. So leaf power graphs have a mean-width at most 1. And also powers of graphs of trees W minus 1 have a mean-width W, and powers of graphs of cliques and most W have a mean-width and most W. So the reason why the I just give an intuition why power is quite well equipped with the mean-width is that like if you have a small separator, if you have like a two separation, and then so previously like you have two separation, but after taking a R power, let's say you have a large induced matching between them. Like these vertices are the matching in the after taking power. But this edge means that you have a path of length R from this guy to this guy, right? And then also this guy has a path of length R from here to here and also here to here. So if the separator is 2, then yeah, the two of them should meet, right? But because of distance, so one of the pairs should have distance at most R. So you have an edge, right? So this is a natural idea, and then we just explore the.
When you add an edge, then the mean width doesn't increase. Does you keep?
No.
No. So what if you keep the same mean width decomposition?
If you just add an edge.
Yeah, you add an edge, and that doesn't increase the induced matching size.
Sometimes it may increase, right? You may create a matching edge for some.
Yeah.
Ah,
Right.
right.
And also very recently, the Vatshelle, Horsfield, Munaro, Pasani, and Palosma. So Palosma had several sequence of works about if you forbid some graphs as induced subgraphs, you have a bounded rank width or not, and they try to think about the Mim-width. And if you exclude the one graph as an induced subgraph, then its a phenomenon is the same. So it's bounded Mim-width depending if it's H is an induced subgraph of P4. But for the two guys, they figured out that the different thing happens. And then they gave us some many interesting open problems. It's difficult to mention here. So you can see the work of them.
We have a comment from the live chat. The H graph is linear Mim-width bounded.
Linear mean width.
Yeah.
Okay. That's well. Yes.
Okay. So this is end of the talk that I want to mention, and then I want to say some various open problems. And first open problem is regarding the finding a decomposition, where that we really think about the approximation algorithm. So is there some approximation algorithm for Mim-width? So even for the running time can be XP because our all algorithms are XP. So n to the some function of Mim-width. So you might have some kind of approximation algorithm run into XP time, but it's quite difficult. So even for the Mim-width one, so is there some constancy such that some algorithm output either the given graph has Mim-width more than 1, or the producer some decomposition of V equals C. So this is quite an interesting problem. Yeah. So Mim-width Mim function is one just says that it's a chain graph, right? So we have to explore something about the chain graphs, but it's quite technical to me. Maybe you can think about this and then figure out something. And then we want to remark that the leap power graphs have Mim-width 1, and then it's a long-standing open problem to find the recognition algorithm for leap power graphs. So probably if you can solve this question in the proper way, then maybe if the graph has Mim-width is more than 1, then you say that it's not a leap power graph. So otherwise you find the branch decomposition, then you can use some dynamic program to recognize leap power graphs. It's kind of possible direction, but yeah, we do not have an answer for the question. Yeah, this is an interesting direction. And also at the very bottom level, so if we if we have some parameter, we want to characterize Mim-width 1 or linear Mim-width 1, but actually we couldn't do that. Even so, we couldn't exclude that as an induced subgraph instruction. So it might be the possible direction. So if you have a student, you can tell him that you can find the list. So I have some of them, but so even for linear Mim-width 1, it should be very simple, right? But it's like you can add you can extend either chain graph, or you can put in the middle of the chain graph and so on, and the ordering gives something like that. But it's
Or obstructions. Or necessary obstructions.
Yeah, some long cycles. And yeah, for the linear Mim-width, like some slightly bigger trees and so on. I have to check the notes. And also some interesting question about can you compute the linear Mim-width on some graphs of bounded means? This kind of problem is natural because like a path width can be computed in linear time graphs of trees 1, and then I and E, so the other line of the compute prove that the linear rank width can be solved in polynomial time graphs of rank width. But we don't know what are the Mim-width ones, so it's it doesn't make sense. Maybe the like we can do for the leaf power graph, like leaf power graphs, or the powers of forest. Can you compute the linear Mim-width there? So very recently, the Telle, Vatshelle, they proved that the linear Mim-width can be computed in n log n time forest. So can you do something for the general forest? This might be maybe doable question. And on the algorithmic side, I was interested in the max cut problem, where you want to find the cut of maximum size. So even for the interval graphs, we do not know the answer. So this in the 2017, Akim and Shalom proved that they solved for the proper interval graphs, but for interval graphs still is open. Yeah, so maybe for bounded Mim-width is quite far from the knowledge. The one comment is that recently the Mamadou Kante and Benjamin Burgos explored the application of d-neighborhood equivalence, and then they observed that the max cut can be solved using the n neighborhood equivalence. You adapt n by d by n. This gives an XP algorithm for rank width, but this gives n to the n algorithm for Mim-width, which doesn't make sense so much. So we don't know much about the algorithmic status for the max cut on graphs of bounded Mim-width. And also the other possible problem is the least variant of locally checkable partition problem, because on the partition problem, you can naturally think about the least variant, like least coloring, right? Least edge color. So you have, for each vertex, you have a set of lists that you have to choose from the list. And then, so we can observe. So recently we observed that least k coloring can be reduced k coloring by adding some k clique. So you have a problem on graph G on the least coloring, but then you can reduce to the k coloring by the adding a k clique, where vertex 1 is adjacent to all the guys without the list 1 and so on. And then because k is a fixed constant, so you add a k clique, doesn't increase the Mim-width too much. Right? By just constant, you can do something. And also observe that H homomorphism there is a known construction, but for every locally checkable vertex partition problem, can you do something? So this is also the general question. Yeah, the other part, the last part is that actually when I met Jan Arne Telle, we introduced another parameter series in the paper with Dong-Yeop Kang and Torstein and Jan Arne Telle. And
this is almost the same, but you look at the cut and then take matchings between the cut, but also you care about the edges inside of each part. So you don't want to have an edges in each part. Yeah. So the funny fact is that the Kodal graphs and co-comparability graphs have unbounded Mim-width, but have bounded Sim-width 1 actually. So we can maybe we can do something for the Sim-width 1. And our question was that the independent set is polymer times solvable. So actually Sim-width 1. Yeah, this is yeah. For the Sim-width 1, we might have a cut like this. You have a whole clique on the left hand side and then click on the right hand side. So you cannot have two matching because they are edges on the each side. Yeah, but we have a restriction, so we can do something maybe. And also another interesting part of Sim-width is that for Mim-width there are not such a related graph, no operation. But for Sim-width it doesn't increase by taking induced minor. So the contraction doesn't, because for Mim-width we forget about the edges. So if you contract something can happen from the inside to the right. But because we care about each part, so it naturally say that the contraction doesn't increase the Sim-width. So can you do some structural result with the induced minor and Sim-width? But if you forbid the C4 as induced minor, you forbid all horse is equivalent. So it's a Kodal, so have a bounded Sim-width. If you exclude C5 as induced minor, I don't know. Yeah. Okay, this is the thanks.
Thank you very much for a very nice talk. Questions? So let me ask you one thing. Maybe just
Sure. So you had many algorithms assuming that the Mim-width is small, right?
Yeah, decomposition of bounded Mim-width is given.
Yeah, decomposition has to be given.
Yeah.
And because we don't have an algorithm to find the
Yes.
decompositions. Do you have some result on chi-boundedness for graphs?
Also bounded Mim-width have high bound. But it's checked by just me. It's not written anywhere.
Okay.
But it's I modify the proof for graphs of rank quiz by Kra and everyone. So it's the same idea can be
like polychi-bound?
Polychi-bound. It's usually generalization of graphs of bounded vectors, right?
Yes.
It's true.
But we know it's true for rank quiz, so.
So you assume that you have some witness for this width parameter, and then your algorithm uses but if you know that the width is at most W, can you find the witness efficient? And what's the how hard is it?
That's also difficult. Yeah. That's also you don't know the algorithm.
Because it has to be polynomial.
Yeah, should be used true, but even if the width is known. But the comment is that for the almost all graph classes by investigated by Belmont and Vatshelle, so like interval graphs, if you have an interval representation, you can give a linear ordering. Yeah.
Okay.
So usually if the representation is given, then you can produce the ordering. So for those graph classes, we can give us decomposition. But I mean that in the general graphs, if you give me any graph,
Is it easy to compute the mean of particular cut? If I give you the decomposition and didn't say what the width is, can you compute the width?
so it's like we need an XP algorithm, so you can test.
Like if I want to say the
so
width is at
minimum.
most k, do you have to try all possible like
To
subset
k
of size k?
So that's why we get the XP algorithm probably images.
I see. And for tree width, there is an algorithm without using decomposition given. Like for instance, if graphs have small tree widths, you know that there's a balanced separator.
Yeah.
And sometimes some algorithm take a use of that fact to have an efficient algorithm. Is it?
Yeah,
Is
I
there
think
something
yeah,
like
the
that?
point is that it's not a submodular.
Yeah.
It does not satisfy the submodularity property. So if you have a second cut on the part, I cannot bound the cut on the next cut and so on. So it's difficult to make the decomposition. So it was difficult, I
see.
if I remember correctly.
And also another question is, so compared to rank width, this is like, to me this is like, in order to have for matrix to have a small rank or large rank, you either have a large identity matrix or large upper triangular matrix.
Yeah.
And one corresponds to induced matching, the other corresponds to the half graph.
Yeah.
And so small Mim-width means that we don't want to have large induced matching, but we allow large half graph.
Right.
Is there some other concept where we allow large induced matching, but only allowing small half graph? Don't allow the large
Twin
half
width.
graph.
Twin width.
Oh, is that what?
Yeah, I think so.
Is that same thing?
Yeah. Okay, not exactly, but it's like we are kind of
You don't want to have
and,
large chains.
Yeah, we don't want to have a large chain for the cut.
Or graphs about this tree.
Yeah, yeah. So chain graph has large twin width, and induced matching has small twin width.
So it's like a two directions,
Yeah.
like expanding the cups of small rank width. Okay. Am I the only one asking questions? No, you asked questions. Any other questions or comments?
Do you have any idea what the relationship between sim width and induced minus multiply? What would be the boldest conjecture?
Large sim width imply something? Or?
Yeah, like a grid structure. You think? I don't know. Yeah, even for C5.
So okay, it's just not much.
Yeah.
Can you find some subgraph when graph has very big Mim-width?
Like a grid? Or
Yeah. Yes.
something like a grid theorem?
Yes.
You mean fixed graph H? So you have some fixed graph H, you want to find the H?
Yeah. Some graph class. If there is, I want to know that there is analog of the grid theorem for the Mim-width.
If your Mim-width is large,
Yeah,
you can
yes.
find something. I don't know. Yeah, but we have some. Yeah, maybe I can comment that for the rank width, you can combine the two chain graphs with different ordering. You can easily make unbounded rank width graphs. So if you follow the rank, the natural ordering for the one chain, then it's mixed with the second chain. But if you have if it's something like this, it's a bounded Mim-width. Right? So you just take ordering of the sky. So it's a bounded Mim for one chain and the other chain. So just sum is small, right? So you have some construction have an unbounded rank width is bounded Mim-width. But I don't know. So what kind of structure can be obtained from the large Mim-width?
Is there an operation preserving Mim-width?
Yes, that's actually explored by this Daniel Palosma's paper. So we found the power doesn't increase too much, but they also in the paper like you put a clique of size k somewhere, it just doesn't increase too much, and also you can delete the vertex. There are some there, but yeah. Some sequence of operations that doesn't increase them too much.
Any other questions? Yeah, if not, let's thank the speaker again.